So last time we met, we used the shift register to kind of control patterns of the lights. We set up a shift register to show the Arduino counting in binary all the way up from 0 to 255, or FF, I guess, in hex. But we really didn't talk a lot about what shift registers do. They're actually quite cool, and that's why I wanted to spend a little bit more time on it. Ours had the same kind of packaging. You have 8 pins on one side, 8 pins on the other. But the question is, what are shift registers really used for? Well, when you want to control a lot of LEDs, our goal today is not to control just 8 LEDs. We want to do 16 LEDs. And we're going to see if we can keep our count going across the chips. We'll have to daisy chain the shift registers together. So on the Arduino board, we have about, I think there's 19 I/O ports. Some are analog, some are digital. But if you want to control like whole banks of lights, say you wanted to control 64 LEDs individually, you certainly have way too many ports than are available on the microprocessor. So what a shift register allows you to do is to expand the amount of output pins you have on the microprocessor. So they come in really handy. So the 3 questions we're going to try to get answers to today are, what is a shift register, why are they useful, and then how do I go about using them? Like I said, shift register allows you to have additional input or output ports added to your microcontroller. Another cool thing it does is it takes parallel information and makes it serial, or in our case, the one we're using, takes serial information and makes it parallel. Remember, serial means 1 bit at a time, where parallel means a whole array of bits at the same time being communicated. So what we do is we take our 1 bit at a time processor and we convert it into a parallel interface. So the microprocessor, in this case, this is the Atmel chip that's built into the Arduino. It communicates to the shift register serially, or 1 bit at a time. Now there's 2 basic types of shift registers. There's SIPO and PISO. SIPO is serial in, parallel out. And then PISO is parallel in, serial out. So you're converting from serial to parallel or parallel to serial. The one we have in our kit is actually a SIPO. We take serial in, but then parallel out. The number on the chip is a 74HC595, which is a very common shift register. You'll find this chip in many types of consumer electronics. The other kind, PISO, is good for controlling a large number of inputs. Say you have a game controller, you use them all the time, and the game controller has so many buttons on it. How does the computer learn which buttons are being pressed at any point in time? The way they do that is they use a shift register to do that. But it's the other kind. The buttons are the pins. You set those all high and then use the shift register to tell this parallel thing. You have all these wires going in, and you want to serialize it so it can tell which buttons are being pressed at a specific moment. Now in our experiment today, we're going to try to get 2 of these to work together. And so we'll have an array of 16 lights and 2 shift registers. So we'll have to combine some parts from 2 different kits. So if we needed 8 additional I/O lines, we can easily chain multiple shift registers together. The way you do that is you connect the output side of the chip to the input side of another chip. Basically, the last bit in the shift register, you wire that to the place where bits wait in line to go into the next chip. So they end up flowing from one chip into the other. We'll see a better example of that in a second. For our project, we need to control 16 LEDs. That would normally require 16 pins from a microcontroller. Our Arduino only has 13 available digital I/O pins. Remember, I/O means input-output. On an Arduino, a pin can be either input or output. With registers connected in series, you can control the 16 LEDs only using 4 I/O pins. In fact, if you daisy chain your shift registers, you can just keep doing that indefinitely, and you still only need 4 I/O pins. Okay, so if you have an old Nintendo NES system and you had a controller and you were to take it apart, one of the chips in there is actually a shift register, and it uses that to communicate back to the game console which buttons are being pressed. Alright, so here's an example of a shift register. We're actually going to try to do this as a group. I need to get more chairs though. This is the demonstration. I always like to try to show physically how these things work using some kind of gimmicky set up, so I'm going to do that now. Just think of these chairs here as shift register. Assume there's 8 chairs there. The first thing you do when you're about to use the shift register is you want to clear it. So say you have somebody sitting in this chair. The first thing you tell the shift register is say, okay, I want to clear out all the bits. I want to set them all to false. So this person goes away, and now all the chairs are empty. So that's that first step. See where it says clear? Those different lines, A, B, C, D, E, F, G, H, there's 8 of them. Those can hold either a person sitting in the chair or not. Person sitting there would represent a 1. Person not sitting there would represent a 0. Now say our ultimate goal is to have this pattern. We want the first light to be on, the third light to be on, and the 8th light to be on. That's what we're trying to get to. That's a parallel setup, right? Because you have all these lines, there's 8 lines here. Problem is our microprocessor is a serial microprocessor. That's how it communicates. So how do we get the people arranged in this order? Well, let's just go through the process. So every 10 seconds or so, somebody rings a bell. Everyone has to get up and move 1 chair to the right. Right now, there's nobody there. But if there was somebody sitting in one of the chairs, the bell rings, that person would get up and move 1 to the right. The bits are being shifted across the chip, 1 at a time. If there's someone sitting over here, like Nick, can you sit here for a second? And then we shift Nick off of the array, and I tell him, go away. Okay? So he just got, that's called the carry bit. Okay? He got shifted off of the end, and now he goes away. Now if we put another shift register here, he would actually go on to the next shift register. That's the one that goes on. But we didn't have that. In the leftmost chair, you have a line here of people waiting to go sit in the chair. And if you want someone to sit there, you get that person in the line and you say, okay, now everybody shift. This person's in line, so they'll sit in the first chair. And so that's what we're seeing right here. There's 1 person in the first chair, the rest of them are empty. Here's the pinout of the actual processor, the shift register. The lines that we were looking at, you figure they put them all on the same side. They don't. But the first one's here, second one's there, and there's the 8th one. So these are the pins that will be wired up to the lights. Now there's a line here called the shift register clock or the serial clock. When you set that to high, and that tells everything in the shift register to scoot over to the left one slot. So that's the bell. That's the, I say when a bell rings every 10 seconds, that's equivalent to what that is. Okay? So the last pin drops out, and the new pin state is defined by the serial pin. So that's the line right here of the next bit you want to go in. If that one's set high, then the first chair is set to 1 and somebody sits there. If that pin's set low, and that's the serial pin, so that's the line of people waiting to get onto the. So when you set this high, the serial clock, it'll look there and to see if that one's high. If that one's high, it's going to set this first chair to 1. So let me just walk through the rest of this then. Clear out the registers, all the LEDs are off. You put in 1 high, that's here. You set the serial line to high, and then you set the serial clock to high, and that first person would be here. And it says move to the right 4 spots. So we'd set the serial to low, and then we'd call the serial clock 4 times. So 1, 2, 3, 4. So I'm in the 5th chair, if I had one here. And I just got shifted over to the 5th chair. Ultimately, we want to get over to the 8th chair. But this next time that we call, we add 1 more high to the front, so we put the serial pin high and call the clock high again, and that will stick another person in the chair. Then the one in the 5th chair will move on to the 6th chair. Now you set the serial line low, set the serial clock high, and that won't put somebody in the chair, but it will still shift everybody over 1. Finally, you set the serial high and the clock high, and then the last person sits down, and all the other people in the line of chairs are now in the right position. Now this would look really bad, right? Because you'd see all these lights kind of flowing through the register if you could actually see it. But the best thing about the shift register is it doesn't actually make these changes until you say, okay, switch the states of the circuit. So while you're building it, you're not seeing it in the lights because you haven't given the go-ahead. You haven't said, okay, I'm done. Now actually change everything. So what you do is there's another pin on the chip called the register clock. And you keep that set to low as you're moving things around over here in the bit register. Once you have everybody in the right place, then what you do is you set that to high, and then the shift register will now display the new setting with the attached LEDs. So you don't see everything sliding over. You do that kind of behind the scenes, and then you set the R clock line high, and then that's when it changes, and you get to see the new setup. So it's kind of a cool thing. Notice that when we put people into the row of chairs, we did it one person at a time. So that's serial, right? But when we show it through the LEDs, we see all the LEDs in parallel. So again, we translated then from serial to parallel, and it allows us to do some pretty cool stuff. Now, if you're into circuitry and circuit design, you can take a look at digital logic. We spent a lot of time on just the basics of that. But if you want to learn how to build chips, like you would see over at Intel, but I know a lot of my friends in the industry who are chip designers or chipset designers. This is what they do all day: is they create microprocessors. They make tons of money, like $120,000 a year. Be a great career if somebody wanted to try that. The way these things work is something called a flip-flop. Inside the shift register, there's a circuit called the flip-flop, and I have a chip that has that on it as well. Now, when you're working with a chip, it's a good idea to go out and take a look at the data sheet. The data sheet gives you all the information about whatever microchip you're working with and pretty much how to use it. So here's the data sheet for the one we've been talking about. Here's the packaging, here's the pinout. There's two different shapes of it. You can either have it this way or you can have it kind of squarish. That's just the packaging. They function identically. Here's the schematics going in. I'm not sure what these ones are. I got to look that up. But I bet you those are flip-flops. Then you have this one, which is the timing diagram. So you have the serial clock being set to high at regular intervals. In our program, we're doing this every 100 milliseconds, which is a tenth of a second. So these pulses are coming out there. Every once in a while, we'll set the serial line to high. Remember, that's the line that's where the next bit you're going to put in the line is located. And then here's the clock. It makes the bit shift register actually display what it has inside it or what you've changed. This is what you do to clear it, I think. But then here are all the actual, you can see the bit being shifted across. So I like the timing diagram because it does show you what the chip is expecting coming in from the other pins coming into the processor. Then they talk a lot about voltages and temperatures and usages. And then finally, the physical characteristics, the actual packaging of it, they have it down to really small, including tolerances. So say you were making some kind of consumer electronics and you had a robot that would put these chips into the board. You need to make sure that the holes are big enough that the legs of the processor will fit into the holes properly. So it shows you all those measurements, how tall everything is. If you flatten them out, this is how long. If you solder it directly onto the board. Here's the square one. Different ways you can attach it to a board. A lot of information. So that's 18 pages for that one chip. Do you have to understand all of it to use it? Not really. But it's nice to know how the shift register works. So let's go out to this one website. The one we're going to do is right here. And there's a video that goes along with this. It does show you the pinouts for doing the daisy chain one. So let's watch the video.